Okay, today I'm going to talk about the challenges of rolling out mine water geothermal heat at scale in the UK. I'm primarily a design engineer with a professional background in the wind energy sector, and I'd like to just share a few insights that I've gained from my work on wind energy projects. My central thesis today is that design reuse in mine water geothermal projects is not only possible, it's also essential for the successful uptake of this technology. To date, mine water geothermal heat projects have tended to be one-offs and to rely largely on bespoke engineering. And this is normal for any emerging technology. But we can't go on like this indefinitely. If mine water geothermal technology is going to achieve its true potential and provide affordable low-carbon heat at scale in the UK, then we will have to get smarter about how we develop and deliver projects. And there are two key challenges. Firstly, building delivery capacity and supply chains, and secondly, reducing the unit cost of heat. So the question is, how do we do this? So what do I mean by design reuse? This slide gives a number of examples in fields ranging from software engineering and property development through to aerospace. Design reuse comes in two different forms or flavors. The first one is simply the repeat production of products to a standard design, as shown in the slide. And the second flavor is the practice of using pre-engineered components in the design of larger and more complex systems. And this practice is routine in all fields of engineering, and there are a couple of examples here. In my experience, the smart design of capital projects involves exploiting both flavors of design reuse in order to reduce costs and streamline processes. Now, this slide gives you three main benefits of design reuse, otherwise known as standardization, in capital projects such as wind farms or other capital projects. To start with, it helps with building a supply chain with lower costs. And this is primarily because contractors find it easier and less risky to do something for the second and third time than they do to do it for the first time. Secondly, it leads to better planning and execution of projects. Project managers can reuse delivery plans and programs from earlier projects and can make revisions and adjustments to iron out glitches and make things run more smoothly. And finally, it facilitates aggregation of data and experience from multiple sites in order to identify common problems and issues. And this information can be used to formulate incremental improvements in the design. So what might prevent us from exploiting design reuse in mine water geothermal projects? And it says here, every project is unique, and I guess that's true. But what do we mean when we say that? Is this really a showstopper for design reuse? So there are some parameters that influence the design of mine water geothermal systems in important ways. And the values of these parameters are site-specific. In other words, they vary from one project to the next. And given this situation, you might well be skeptical about the idea of using design standardization. And that's quite a reasonable position. However, certain key elements of the system are amenable to standardization while still allowing for parameter variance between sites. And I'll come back to that point in a little while. On the next slide, I'm going to outline some strategies that, in my experience, facilitate design reuse and maximize resulting gains. But before we get to that, it might help to be a bit clearer about the sort of area of focus for these strategies. Now, there's a health warning here. I'm primarily a plant designer, so I don't know a lot about underground engineering. I don't know much about heat network design. There are other people in the room who do. The principles and strategies of design reuse can be applied to all parts of a mine water geothermal system. However, the biggest benefits are likely to be gained, in my view, by focusing on the central facility, which, let's call it the heat hub. And in a moment, I'll be talking about the idea of a reference design. Now, the heat hub is the element of the system where, in my view, this idea has the most obvious relevance and appeal. But I suspect it could be applied elsewhere as well. So, here we come to the strategies. Firstly, develop a portfolio of similar projects in parallel. The shared aims and requirements of these projects will indicate the scope for design reuse and should directly inform the next strategy, which is to develop a reference design. Now, this is a blueprint for how you intend to realize your projects. So it includes a set of outline physical plans and functional specifications, but the really key part is a well thought out construction plan and a set of procurement scopes and interface definitions to facilitate delivery. So who's going to do what, who's going to build what, what's it going to look like, when are things going to happen, those kinds of questions. Thirdly, engage with contractors and suppliers in a strategic way. Show them your pipeline of projects and be clear that repeat work is very much on the cards. It's not going to be just a single project. Don't issue tenders on a project-by-project basis. Use frameworks so that you're gaining that benefit of repetition. And finally, embed learning by doing. Don't reinvent the wheel. During project execution, ensure that plans are reused and refined and that lessons are learned. And apply that principle to other processes as well. And before I wrap up this general discussion, I'd like to make a final point about the need for institutional actors to carry forward the work of developing and delivering mine water geothermal projects. Now, as I see it, these institutions will have to work in a coordinated way and with some kind of a public accountability. And I think the example of Gateshead Council and the role, the benefit of their local residents' knowledge and trust in the council is a really good example of this. Moreover, these actors, these bodies will need to be both durable and trusted. Trust is the vital factor here. Householders and other customers will only sign up for mine heating if they have faith that the infrastructure and the organisations that operate it are going to be in it for the long term. So there's some food for thought. Anyway, after that slight digression, we'll come back to the question that I posed a couple of slides back. How can a standard design solution work for different mine water projects given the variability of parameters such as the mine water abstraction temperature? And to answer this, we're going to dive into the world of heat pump design for a minute or two. Now, we all know that heat pumps play a vital role in mine water geothermal systems. What I'm going to show you is that they're also quite flexible devices that can operate reasonably well across a range of conditions. Now, how many refrigeration or heat pump engineers are there in the room? That's good, because in the land of the blind, the one-eyed man is king. So if, this might look a little bit intimidating, but don't worry, things will get better after this. This slide shows the thermodynamic chart for anhydrous ammonia, which is refrigerant 717, commonly used in large heat pump systems. And I've drawn two heat pump cycles on the chart. And in both of these cycles, the compression process results in a fourfold increase in the refrigerant pressure. So this means that the two cycles will both work using a compressor that's optimized for a 4:1 pressure ratio. And as it happens, it's also possible to design the evaporator and condenser systems such that they can also accommodate either cycle, and for the same price, you also get any intermediate cycles within with a 4:1 pressure ratio sitting between cycle 1 and cycle 6 here. So it's possible to design a heat pump that can work at different pressures, so long as we keep the pressure ratio of the heat pump fixed at 4:1. Now let's look at how this flexibility relates to the temperature of the mine water heat resource. And what we find is that each cycle fits a particular mine water temperature. And as the chart shows, this temperature decreases from 35 degrees to 14 degrees C as we move from cycle 1 through to cycle 6. So for any given mine water temperature in this range, our standard heat pump design can give you a cycle that fits that temperature. Now this slide shows how the overall performance of the heat pump system varies between cycle 1 and cycle 6. And in cycle 1, the heat supply capacity capability is 2.85 kilowatts for each volumetric unit of flow capacity at the compressor suction. And then as we move from cycle 1 to cycle 6, that capability drops away by more than 40%. But the coefficient of performance of the cycles is much less variable. And what you can see is that as we go from cycle 1 to cycle 6, the COP actually increases slightly, although there is a reduction in the supplied water temperature from nearly 80 degrees to just below 50 degrees. So to conclude, the main point I wanted to get across today is that it is possible to design an industrial heat pump that will work efficiently across a range of different resource temperatures. Now, to my mind, this opens up the possibility of developing a standard heat pump specification that could work in more or less any mine water geothermal heat application. So I'm hoping that this example will persuade you that the supposed uniqueness of mine water geothermal projects does not mean that we have to resort to bespoke design for every project. Remember, design reuse is our friend and our tool if we want this technology to succeed and to deliver its capability. Thank you all for listening.